Hello everybody, I'm Anand Raj. VR Group 4 and 3C has been assigned to analyze a DC circuit with dual source and AC series parallel circuit. On selection, we have been assigned to make a report on what circuits we are referencing off. We are not allowed to use circuits from lecture slides, but only those from online sources. The DC circuits we have selected is from page 49, example 3.4, figure 3.10b of the textbook of Engineering Circuit Analysis 9th edition. Some modifications are required to meet the assignment requirements, one of which is having a 4 resistor and 2 unknown variables, which can either be current or voltage. Since the textbook already has solutions for the particular circuit, it is only more meaningful to change the arrangement of the resistor a little.
Hi everyone, I will be introducing our selected DC circuit. Our best circuit was edited from textbook, but we made several key modifications to fit this assignment. First, we set the voltage source as 6 volt and fix the current source as at 5 milliampere. Then we scale all resistance value by a factor of 100. So this will become 800 ohms, 1000 ohms, 400 ohms, and 200 ohms. And then it will be relocated to be in parallel with the voltage source, like this. Okay. This adjustment keep the branch currents within the practical milliampere range. And as shown on the screen, this is the final circuit.
Hello, my name is Kavanish Anarchy Kumaration. So today I'll be actually explaining about DC theoretical calculation. So in order to find VTH, we have to open circuit at terminals A and B to find VTH. So VTH is equals to V source 6 volt plus with voltage of 800 ohm resistor, and then we'll get 10 volt. In order to find RTH, we have to turn off the sources. For current, we open circuit, and for voltage, we short circuit. And then for this is our Thevenin equivalent circuit. This is our Thevenin equivalent circuit with load connected. So in order to find I2 is the current flowing across this 1000 ohm resistor. So I2 is equals to 5.56 milliampere. To find voltage across the 800 ohm resistor, we need to find VA. So VA is equals to 5.56 volt. We use Ohm's law, and then for this, we just take 6 volt minus with VA. And in order to find I1, we use KCL and also Ohm's law. So after we using KCL and Ohm's law, we got 30.56 milliampere. That's all for Thevenin's theorem. Okay, moving on to Norden's theorem. So in order to find IN, we are using Ohm's law and also KCL. So after using Ohm's law and KCL, we got the answer for IN, which is 12.5 milliampere. And for RN, we have to find Rn. Rn is also same as RTH, as we already calculated RTH just now. So Rn is equals to RTH. RTH is equals to 800 ohm. So in order to find I2 flowing through the 1000 ohm resistor, we will use current divider rule. So after using current divider rule, the answer was 5.56 milliampere. Again, we have to find I1. So we used Ohm's law and also KCL to find I1. So current in is equals to current out. So I1 is equals to I3 plus I4. So when we calculate using Ohm's law and KCL, we'll get 30.56 milliampere. That's all from me. Thank you very much.
After finishing the manual maths, we built the exact SAM circuit in multisim to verify our rods. If you look at our comparison table right here, you will notice that our simulate value perfectly match our hands calculation. We achieved an amazing 0% error across all primary parameters. This flawless result proves that our analytical approach and our understanding of DC circuit law are 100% accurate.
For the AC circuit, however, we used an example circuit from the website called LiboText. It is from a tutorial under nodal analysis, especially for AC circuits. We had to follow the assignment and remove the AC current source and replace the 250 ohm resistor as a 25 millihenry inductor. We will be analyzing the voltage and current across the 500 nanofarad capacitor, current across the 25 millihenry inductor, and voltage across the 400 ohm resistor. That's the circuit we are going to solve for. And let me allow my teammates to explain how we solve these circuits. Thank you.
Hello, my name is Lex, and I'm going to be showing you how we solve this AC circuit and the values of IL2, VC, and IC, VR2, these values right here. So I'm not going to show you exactly the step-by-step process on how we do it, but I'm going to tell you how did we do it because time is limited. Okay, the first thing we do is that we need to know omega, the value of omega, so we can convert all of these values into their respective inductive forms, because as you can see, this is in ohms, this is in Henry, and this is in farads. So right now that's a problem because, as you know, in basic algebra, you cannot just slam in multiple different units into an equation and expect everything to add together. No. I mean, unless it's multiplication, then something might work. But this is addition, basic arithmetic with addition. So we cannot just do that. So what we do is that we find the respective impedances and we redraw the circuit, assuming that they're all just resistors with complex number resistives. Yes. Then what do we do next is we first have to find the total. We first find the total current. Total current is in a polar form where there is actually a phase difference. So in this, we first need to add these two together to get the so-called inductance at that region. So now we only have two resistors in this, not inductors, one big impedance in this region. Then we can add parallel these two impedances together, as you can see right here. Then we can find the impedance of this entire thing. So what we do is we converted that section into something like this, where everything is in impedance. 1, 2, 3, 4, 5. Okay, then what do we do? We just add them all together because it's a series, so that's what happens to resistors in series. Then we take the 20 volts divided by that, we get the total current. With the total current, we can find the voltage at this point very simply by just taking the total impedance at this point, multiplying it, total impedance at this point multiplied by the current, and we will get the voltage at this point. Then with that voltage, we can find the current here, we can find the current in this region. Then with that information, we can find the voltage at this region. Going through all the tedious steps, we can figure out that IL2 is this, VC is this, IC is this, and VR2 is this. Thank you.
Hello everyone, my name is Harry Rickson and I will be explaining the AC simulation and the phasor diagram. So after completing our manual AC calculations, we recreated the circuit in Multisim as we can see here. Okay, and then we performed a single frequency AC analysis at 2000 Hz to obtain the branch currents and component voltages. And the analysis here shows the values such as the current through the inductor IL2, the current through the capacitor branch IC1, and the voltages across the capacitor and the resistor. These values closely match our manual calculations. So here we can see the voltage phasor diagram illustrates the phase relationship between the source voltage, the resistor voltage, and the capacitor voltage. Each phasor has both a magnitude and a phase angle, allowing us to visualize how the AC voltages are related. And now similarly, we can see in the current phasor diagram, it shows the relationship between the IL2 and the IC1. Because the circuit contains reactive components such as inductors and capacitors, the currents are not in phase and appear at different angles. So finally, when comparing all the simulation with our manual calculations, the results are almost identical, and the only difference is a very small 0.02% error for IL2, which is due to the rounding during the manual calculations, and this confirms that our theoretical AC analysis is accurate. Thank you.
Hello, my name is Shashivarman Tangelu. In conclusion, this assignment successfully applied DC circuit theorems to analysis both DC and AC circuits. Manual calculations were verified using Multisim software and the results were high accurate. For the DC circuit, Thevenin and Norton theorem simplified the analysis with manual and simulation results matching perfectly 0.00% error. For the AC circuit, phasor algebra accurately solved the circuit parameters with only a minor 0.02% error due to rounding. Overall, this project confirmed that manual circuit analysis is reliable and reinforced the importance of circuit theorems and impedance analysis in electronic engineering. That's all from me. Thank you.